Now, I think last time what we did was on sampling and sampling distribution. That's true. So today, then I want to go to the next item, which is inferential statistics, basically generally for hypothesis testing. And the first one will be basically an introduction to the concepts that are used in hypothesis testing. Now, in research, you normally, and I've repeated this many times, undertake studies based on a sample. You collect data based on a sample. First of all, you define the problem that affects a population. Then you draw a sample from that population to be able to study that problem. You collect data on the sample. You analyze data still based on the sample. Write a report, interpret your results, and write a report again based on the same sample. Then you generalize for the entire population. That's usually the research process. You generalize for the entire population. Now, hypothesis testing involves making a guess about a population characteristic using sample characteristics. So you draw a sample, say, from this class of size 10. You calculate the sample mean to enable you to test whether the population mean, there might be some claim about the population mean, whether the sample mean is equal to that population mean. Now, hypothesis, by definition, the simplest definition of a hypothesis is that it's an educated guess. It's a guess all the same. You guess it. You make a guess about the population characteristics. But it's educated. Why educated? Because you need evidence to test that sample, to test that claim, that guess, to test that guess. So the evidence, you can only draw evidence from the sample by collecting data, analyzing data, and testing whether the guess you made about the population is true. And this is widely used in social sciences, even in pure science. You widely used hypothesis, even in medical sciences, whatever, agriculture, name them. People hypothesize, then they collect data from a sample, then they test some behavior of the population. Now, hypotheses normally are stated in pairs. You state hypothesis in pairs. The first hypothesis you test, you state from a position of neutrality. You remain neutral. So that hypothesis, which is stated from a position of neutrality, is called the null hypothesis. Null hypothesis, which you state from a position of neutrality. And it's normally denoted by HO, or H subscript naught. So when you see a H subscript naught in the context of hypothesis testing, we know you are talking about the null hypothesis. So it's stated from a position of neutrality. You remain neutral, and we will show you how you remain neutral when you are stating the null. Now, then you collect data to test. There is another hypothesis. If you reject the null hypothesis that is stated from a position of neutrality, you must have an alternative hypothesis that you can accept. So that hypothesis, which is contrary to the null, the one you are testing for, is called the alternative hypothesis, denoted by HA, H subscript A. Sometimes it is normally called, in fact, the research hypothesis. That is the research hypothesis. It is the hypothesis you state from the statement of the problem. It's written from the problem. The problem will give you the alternative hypothesis. Always. Then, of course, you'll have its equivalent null, which is stated from a position of neutrality. So always you check whether you are you ensure that you know the alternative. But you need to take note of the disclaimer that different universities have different ways of stating the hypothesis. Some say you only state the null because the alternatives is implied. Some will say you state the alternative because the null is implied. At USIU, I know you only state one. But when you state one, you know the alternative. You must know the alternative, which you will accept when you reject the null. When you reject the null. So, for example, this is a case of a sleeping pill. A sleeping pill manufacturer claims, the manufacturer claims that when you take the pill, you sleep soundly for 4 hours. That is what's written in the pill bottle. So you go to a pharmacist or a chemist, you buy the pill, you check on the label, they'll say that when you take this pill, you sleep soundly for 4 hours. That claim is about the sleeping time of the entire population. The sleeping time of the entire population. People use it. Then, the users, feedback from the users. I'm defining a problem now. Feedback from the users can only indicate that either of the following 3 scenarios. Majority of the users may be saying that despite the manufacturer's claim that the sleeping time is 4 hours, they are sleeping for less than 4 hours. Majority. So that's the problem. Alternatively, majority of the users may be giving a feedback that when they take that pill, they sleep for more than 4 hours. So it means the manufacturer's claim is not true. Either way, whether they sleep for less or sleep for more. So the first pair there, H naught full colon, that's the way you write a hypothesis, is mu is equal to 4. You are stating mu from a position of neutrality. Mu is the population mean. You are stating it from a position of neutrality. Against HA, the problem, mu is less than 4. They're claiming they're sleeping for less than 4 hours, if that was the issue. And the other one, the other problem where they were claiming that they're sleeping for more than 4 hours is the second pair. Mu is equal to 4. Against the alternative, which is the research hypothesis, mu is greater than 4. Alternative, the users may have been claiming that their sleeping times vary. Sometimes they sleep for 4 hours, sometimes they sleep for less than 4, sometimes they sleep for more than 4. So there's no consistency. Now that is the last pair. Again, mu is equal to 4. You state that hypothesis again from the position of the manufacturer, neutral. Against the alternative or research hypothesis, mu is not equal to 4. Now, these relationships of the alternative, less than, greater than, not equal to. Now it gives you two types of hypothesis designs. The first 2 pairs is called one-sided hypothesis, one-tailed or one-sided hypothesis design. But one-tailed is a better term. Why is it a better term? And I'll tell you what that tail means. It means the tail of a normal distribution. The normal distribution tail rolls from left to right symmetrically. So when it is less than, it's the left of the line of symmetry. When it is to the right, it is the right of the line of symmetry. And you'll see how that is used. Well, the third one there is called a two-tailed hypothesis design. A two-tailed hypothesis design, which essentially means that you're using the both tails of the normal distribution curve. And again, you'll see how that works. That's why we did, part of the reason why we did normal distribution. Now, when you write a hypothesis based on a population parameter, population parameters are all the summary statistics. The mean, the median, the modes, geometric mean, harmonic mean, skewness, standard, all those. If you write a hypothesis around a population parameter, like this one we have designed it around the population mean, then the second this thing was wearing off. So if it's around population parameter, then that is called a parametric hypothesis design, which will require the use of parametric tests. These are called parametric hypothesis designs because they're designed around population parameter, the summary statistics. In this case, the arithmetic mean. Then that is parametric hypothesis design, which will require parametric tests. And you will know what parametric tests are in future. But if they are not written around the population parameter, then they are called non-parametric hypothesis design. So I invite you to go and check online even the differences between parametric and non-parametric tests and their examples. Parametric and parametric tests and their examples. Just go briefly and check those the concepts. Now, types of errors you can commit when you are testing hypothesis. Remember, you're using a sample. The sample you're using is based on a population, is based on some population. There's a likelihood that your sample may lead you to draw wrong conclusions, may lead you to say, number one, reject H0, the null hypothesis. When the null hypothesis is true, the data you collect for using a sample to test the hypothesis may lead you to reject the null when the null hypothesis is true. When you reject the null, when it is true, as informed by your sample data, you commit an error. That error is called type 1 error, denoted by Greek letter alpha. No other letter. Type 1 error is noted by alpha, this one. The other name of type 1 error is false positive. False positive. But the most commonly used name in hypothesis testing for type 1 error is the level of significance. Level of significance, alpha. And the level of significance is the probability of rejecting a true null hypothesis. The probability of rejecting a true null hypothesis. Rejecting a true null. So this is one of the errors you can commit. However, when you reject H0, because it's H0 you are testing, when H0 is false, there is no error. That is a correct decision. The other area is acceptance. You can accept H0 when H0 is true. When you accept H0, when H0 is true, there's no error you have committed. But when you accept H0, when H0 is false, you have committed an error. And that error is called type 2 error, denoted by Greek letter beta, sometimes called the power of the test. The power of the test, or false negative. There are other names for these two errors, which I will show you through that example. So you have type 1 error which is the level of significance, and type 2 error, which is the power of the test. We're not going to bother with type 2 error until the end of this topic. This is hypothesis testing. The error we will be concerned with is this error. You want to minimize the likelihood of rejecting a true null hypothesis. That's one of the major objectives of hypothesis testing. So I want you to keep this error in mind, these two errors in mind. Now, rejecting a true null. So let's go to the example I gave you here, this one. Suppose this is the hypothesis you are testing, this one, the first pair, this one. Then your sample data leads you to reject H0 when H0 is true, meaning the manufacturer's claim is true. But the sample data you have collected to test this claim is leading you to reject it when it is true. When you reject a type 1, when you reject a true null hypothesis, then the error you commit is actually the consequence of that rejection is to the manufacturer, because you're telling the manufacturer that their claim is faulty, and hence the likelihood of removing the pills from the shelf is very high. So type 1 error is sometimes called the manufacturer's, the producer's risk. Is the risk to the producer? Is the producer who will suffer? Whichever circumstance, when you commit type 1 error, it will be the producer's risk. While when you commit type 2 error, you are accepting a false null. You accept a false null, meaning that you are accepting the manufacturer's claim of 4 hours, and it is false. But your data leads you to accept it. The error now you commit, the consequence now is to the consumer. So type 2 error is sometimes referred to as the consumer's risk. The consumer's risk. So I'm just giving other names for these errors. Type 1, therefore, can be this one. Type 1, therefore, can be false positive, level of significance, or producer's risk. Type 2 error can be power of the test, false negative, or consumer's risk. The most common term used in business reporting is the producer's risk and economics, really. Producer's risk and consumer's risk. So that's critical. Those errors, and you need to know them, and you can review further examples of type 1 and type 2 error. This ones I've talked about. I'm going to belabor that. That's another example. In a criminal trial essentially is an example of hypothesis testing anyway. But this one is faulty. Just remove this without statistics. It is a form of hypothesis testing. Of course, not without statistics. A form of hypothesis testing. In a trial, normally, in any trial, lawyers know better than we do. The judge or the jury, whatever the case, must decide between only 2 hypotheses. Even in Kenya, the accused is presumed innocent. That is the null hypothesis, stated from a position of neutrality. The alternative, the defendant is guilty. That is the alternative. Then you collect data. You collect data to test this hypothesis that the defendant is innocent. Because that's what you are testing for it, that the fellow is innocent. Where do you get the data from? Where do you get the data from? Let me ask. Where do you get the data from?
Witnesses.
Eh?
Witnesses.
Witness testimony.
Evidence.
Evidence.
You're not clear.
Sorry?
From past
Data.
judgments.
Where do you get data from to test this hypothesis?
Past judgments.
Witnesses.
Witnesses.
Evidence.
Essentially, that is the role of the prosecution. The role of the advocates. They generate data. They generate data. to be able to test for the null. Then suppose that after they presented their data, wherever they are, their data or arguments, they go on and the judge makes type 1 error. The judge makes type 1 error. He is rejecting a true null based on the evidence so far gathered. He is rejecting a true null, meaning the defendant is innocent, really. But because of the data that has been generated, the defendant is guilty. So he's sending an innocent fellow to prison. That is committing type 1 error. And again, it is still the producer's risk, because you are populating. It is the producer's risk. The producer is the judge, the whatever, where you're sending. Or you commit type 2 error. Type 2 error is that you are accepting a false null. Accepting a false null, meaning the fellow is not innocent. The fellow is not really innocent, but the data gathered gives you, enables him to or her to release the fellow. So the guilty are free. That is type 2 error. That is type 2 error. And you can list as many as you wish, or examples of these types of errors. Business or any other area, social sciences, pure sciences, health, name them. You can, without an issue. Now, that's what I've done there. All those stories I've talked about. I talked about those stories. Now I'll go to you the steps that you must follow while testing any hypothesis. Any hypothesis. There are actually 6 steps, because 2 and 3 can be combined. The first thing you do when you want to test hypothesis is to describe in words the population characteristics about which hypotheses are to be tested. In research, this is what is called the statement of the problem. You state your problem. You state the problem. Like I stated the problem that the users who consume the pill are complaining that they don't sleep, they sleep for less than. I'm describing it in words. Then number 2, you state the hypothesis, both the null and the alternative. So you take H0, like in our case up there, mu is equal to 4 against HA, mu is less than 4. Say. Then number 4, you display the test statistic. That is the criteria for rejecting or accepting the null hypothesis. You display it, and I'll show you. We have done it in the interview. I'll show you what a test statistic is. You display it. Then collect data. That's where you collect data from a sample to calculate the test statistic. You collect data from the sample to calculate the test statistic. The number 5, the first thing you do, you set your level of significance. You set your level of significance, your own alpha. Alpha is normally a percentage. In business, we normally use alpha of 5%. The probability of rejecting a true null at 5% in business. Type 1 error. That's alpha. So you set your own. In pure science, engineering, medicine, all pure sciences, alpha must be very small, because you're not supposed to commit an error. You're not supposed to reject a true null in those sciences. So pure sciences, alpha normally is stated at around 3% or 1%. Some using 1%. In medicine, 1% is stated. 1%. So that you ensure that you don't commit type 1 error. That's what I mean by very small. But business, you know, is the bottom line is profit. Because you see, the lower the level of significance, the lower the level of significance, the costlier the investment you put in, the costlier the investment you put in. If it's in medicine, it's a treatment regime, then you must invest heavily. So that the likelihood of somebody like a pill, not people not sleeping as prescribed, is almost zero. But in business, profit is the bottom line. The lower the investment, the higher the margin. So they would rather set the level of significance very high. Some people will set it at 10%. So you set your level of significance, alpha. Then you determine what is called the rejection region. The region where you are going to reject the null, called the cutoff region, where you're going to reject the null. Depending on whether it was, depending on the type of test. Then lastly, you state your conclusion. But you state your conclusion based on the problem in one. You go back to a problem in one, then now you conclude. You conclude on the basis of the problem in one. Don't just say reject the null or accept the null. No, you state, you draw your conclusion based on the problem in one, and you will see how that is done. You see how that is done. So any question up to there? Any question? That's the introduction.
Yes, Prof. I have a question.
Yes, please. Okay, you are very. I'm not hearing you clearly. What's up?
It must be your side because we can hear them clearly.
You can hear me?
We can hear you and we can hear the other attendees clearly.
It's me who can't hear me you clearly.
Can you hear me now?
Just ask, probably I will hear.
Okay, so I was wondering, you've just said that the null hypothesis is from a point of being neutral. But then in the criminal statement, you said that the criminal is
I'm
innocent.
finding it difficult to get you actually. What's up? Are you getting me clearly myself?
Yeah, I can hear you.
Yeah, but move closer to your,
Guys,
to
can
your
you hear
mic then, because me, I can't get you actually.
Guys, can you hear me?
Very well.
Unless, hello, who is louder? Okay, just say, I will ask. Just ask. Somebody will.
They
make
can
it
hear
louder.
me. Okay, I'm asking.
Yes.
You said that the null hypothesis is from a position of being neutral. But then when you stated the null hypothesis for the criminal, you said that the criminal is innocent. Is that being neutral, or is that that you've decided that he's innocent? Is that being neutral?
Anybody who
Or
got it
is it
clearly? George.
Maybe I can assist. Yeah, so using legal jargons, you are innocent until proven guilty. So the null hypothesis when you go to court is that you are innocent. What the court will adjudicate is to try and prove you are guilty. So if the judge rejects the null hypothesis, which is this is an innocent person, so that's the null hypothesis. So if it's rejected, then he has sentenced an innocent person, so meaning he has rejected the null being innocent, and confirmed that he's guilty. And in the other scenario, if you are using the alternate hypothesis, where he sets free a guilty person, then he'll have committed the type 2 error. I don't know if Glo have helped answer. The hypothesis is that you are innocent. So by sentencing the person, an innocent person, meaning he has rejected the null because the null was innocence.
Are you sorted?
maybe you can use another example, please. If maybe if it was in manufacturing and you want to decide if a product is defective or not, what would have been the null hypothesis, the product is not
That-
defective.
The null hypothesis will.
No. Just say that. Say again.
Maybe in manufacturing,
Yeah.
what would have been the null hypothesis? Would you say that for your null hypothesis, the product is not defective, and then now you go to your alternative?
No. I get you. Now I get what you say. I'm getting it. You see,
Your product.
I stated this. You state the hypothesis about a parameter. And I said here we can have a population mean. You can have a population mean. You want to look at what is it about that manufacturing you are concerned with? What is it? Just tell me, what is it you are concerned with?
I want to know if the product is defective or not.
Which product? What effective in terms of what? How do you measure effectiveness?
Defective, a product with defects.
In
It won't
terms
function
of,
well.
in terms of
Whether it will function well when it goes to the market.
eh?
Whether it will function properly when it goes to the market.
But you know, all these things, you know, in statistics, you must measure. You know the levels of measurement,
Mm.
You remember the levels of measurement,
Uh-huh.
What are you going to use to measure effectiveness, What are you going to suppose? What you see, like let's say this sleeping pill thing, That's a manufacture. It's manufactured, isn't it? It's manufactured, And you have to check whether it's effective on sleeping time, So this fellow, what the fellow uses as a measure is the sleeping time. Sleeping time, if that is the issue, Now, in your case, therefore, whatever you are, if you are looking at the effectiveness in quotes of that product, whatever it is, then there must be a measure which you are going to use to test for. Is that measure you are testing for? And you write the null hypothesis, the alternative around that measure you have tested. You have identified. So in your case, therefore, so now let me to clarify this. I said that you can write a hypothesis based on a population parameter. Based on a population parameter, those summary statistics. You just a minute, I'll come back to you. A population parameter. But those are told you, those are called parametric designs. But there are also others called non-parametric. Let me tell you, you can decide, and we'll do it here. You want to check whether there is a difference between say in terms of performance in examination. You want to check whether there's a difference in performance, the difference between male and female in exam performance, male and female. So you collect data on all students. Then you split your data into two. Then you say you want to check, suppose the claim here is that females perform better than males in a typical exam. That's the claim. Then you collect data. You collect data on students' performance. There must be something you are collecting data on student performance. Then you check whether it's a difference between male and female based on the marks scored. So there must be a measure. That's the critical thing. You must be a measure that you are using to test your hypothesis. Is that clear now?
Yeah.
Yes, George, your answer up,
Thank you.
Oh, sorry. I wanted to give an example in manufacturing that perhaps could have tried to help clarify the null position, where you have a scenario of a claim that in a factory, assume it's a soda factory, where someone claims that not all bottles are filled to the max, like maybe they are producing at 1 liter. So the null hypothesis will be you are testing the claim to confirm that indeed, you can pick a sample to confirm that indeed all bottles are either filled to the brim, which would be alternate, because remember the claim is not all bottles are filled to 1 liter. So your null is confirming that claim, and then now either accepting or rejecting the claim.
Sawa. Sawa.
So,
Good.
Haya.
Now we are starting now on parametrics now, examples of parametric tests. And it's very important that let's pay close attention here. The first one, and I want you to note this elsewhere somewhere. The first test I'm going to deal with is test for single means. Single means. We are testing around the population parameter. These are parametric tests. Testing for a single mean. We're only doing for the mean. You can then generalize for any other summary statistics. Any other, whatever you want to test for. Test for single means. They also single proportion. But I'll just look at the mean here. Then, of course, you can now generalize for the others if you wish in future. But for this course, we just want to be single mean because we cannot do all of them in this course. Just do what you can now then generalize for others. So test for single means. That one. Test for single means. Now, I'm going to give an example here. And I want to use an example rather than just going through this theory. I use an example. Just take this example. And please take a pen and a paper. I'm going to change this problem. I want to change this problem so that we comprehensively cover this. The School of Business, say at USIU, has been accused of grade inflation for its marketing measures. So the students are complaining that the GPA of marketing students seems to be higher than the GPAs of every other business student. That is the problem. You have stated the problem. The GPA. GPA is measurable. So these students are saying, oh, we have checked around, they have found that GPAs for marketing students are higher than those of the higher of the other students. So they're blaming the school for grade inflation. They could have blamed it for grade inflation. Inflation means that that the marketers are scoring lower than the others. But this is graded inflation. Now, there must be many factors here, I can tell you, that may make marketing measures perform better than the other measures. They could just be bright students. Bright students. The marketing option may be an easier option. Or grade inflation could be one of them. Or there must be some attribute among marketing students that make them perform better. Probably one gender is performing invariably better than the other gender in the other groups. So there are many factors. But these students are complaining just on one thing, grade inflation. Now, you cannot just accept, the registrar or the university cannot just accept that blanket claim by the student population. They can't accept. So they commission a researcher to check this claim about marketing measures. So the researcher will have to collect data from marketers, get the average grade for marketers, then compare it with the general population. Then draw conclusion. But after you have done hypothesis testing, you decide that you are going to use test for single means. Now this is then the issue. Now I've defined the problem. Now step one, and I want to write this down. I've defined the problem. The problem is here. Number two, we state the hypothesis. Stating the hypothesis. In this problem, the hypothesis was that the general population GPA is 2.7. 2.7. Yeah. Mu is, so write H naught, full colon, mu is equal to 2.7. H naught, remember the way we wrote it. H naught, full colon, mu, I hope you are writing, H naught, full colon, mu is equal to 2.7. That's the alternative, that is the what? That is the null. You are stating from a position of neutrality. Neutrality, that is H naught. H naught full colon is a subscript. Mu is equal to this. Mu is equal to this. Don't look at any of the data on this slide. Just look at this, what I'm doing here. Mu is equal to this. But they're accusing this fellow of great inflation, so HA, full colon, mu is not equal to. So it's not equal to. So you write this and cross this one here. You cross it. No, sorry, great inflation. So mu is greater than 2.7. So this is greater than 2.7. That is great inflation. If it was great inflation, mu would have been less than 2.7. So this is your step 2 and 3. You have stated the null hypothesis and the alternative. And this is a one-tailed test to the right. One, because of this greater than. If it was deflation, there have been one-tailed test to the left, less than 2.7. It was two-tailed, this one would have been mu is not equal to 2.7. So you have stated your hypothesis based on the general population mean. Then go to step 2. Step 4. Step 4, and I hope you're writing this. Step 4 is to display the test statistic. Display the test statistic. Now,
Prof.
Note that the test statistic is dependent on whether the sample is large or the sample is small. And note that, and it's important to note that the test statistic is stated depending on whether the sample is large or the sample is small. And I want to ask, we have talked about this in the past. What is a large sample? We were discussing last week. What's a large sample?
Greater than
Greater than 30. But greater than or equal to 30. So note that when the sample is large, then the test statistic is the Z test statistic. Z. The Z scores, is the Z test statistic when the sample is large. However, when the sample, the sample is the test is the Z test statistic given by the following. This is the Z test statistic. Is here. Where are those stories? It is here. The Z here. It is here. This one. And but this one is a small n. Small n. This one, we had this last week, when we were standardizing the means. So that is the Z test statistic. Z is equal to X bar minus mu over sigma divided by root n. We have this last. That is the Z test statistic. That is the Z test statistic when the sample is large. And when the sample is small, that is less than 30. When the sample is small, less than 30, then the test statistic is the student T test statistic. The student T test statistic. And the student T test statistic is given by the same thing. I can tell you, the same thing. They just change this one here to T. This one. T is equal to this. In some text, you'll get it put here T minus N minus 1, like that. But just use N. Just use N. I even know in this one I've given you N minus 1. In some cases, just use N all through. Don't worry. Those are these mathematical details. So this is when the sample is small, you use the student T test statistic. You see, like in this case here, I've given you n minus 1. Just use n. Just use n. Forget about when the population and sigma is known. Those are details. Just use over root n. So that's the test statistic. So you display the test statistic. Actually, display and compute the test statistic. Display and compute the test statistic. That is in step 4 of hypothesis testing. So when you compute it based on sample data. You compute it based on sample data, the data you have collected. So you collect some data to be able to compute the test statistic. The test statistic to test this hypothesis here, this one we have just stated here. So we are going to collect data now to compute that the test statistic when the sample is small and when the sample is large. And I'll use the two cases. I hope you are noting this because we want you to note them down. So these are data you have collected now from a sample of marketing measures. You collect a sample from marketing measures. And the marketing measures, and let me just, I'm coming back there. I want to share Excel quickly. That we are okay with it. Share Excel very quickly. To enable us compute the test statistic. So this is my data I've collected. I'm sharing Excel. Share this. Sharing this, but it's not delaying here. Not share yet, eh? Why is it hanging here? Excel. Share. That's my Excel. So I want to do two cases here, eh? Kill two birds with one stone, eh? I'll make this one larger so that you see them clearly. I want to kill two birds with one stone. So this is the data I've collected from marketing measures to test that hypothesis. So this column here are the GPS, X are the GPS, F are the number of students. This case A, largest sample. This is the largest sample case. Largest sample. Large sample. So the GPS normally are from 1 to say, let's take simple cases, 1 to 1.5, then 1.5 to 2, then 1.5 to 2, to 2, 2, then 2 to 2.5, 2 to 2.5, then 2.5 to 3, 2.5 to 3, then 3 to 3.5, then 3 here to 3.5, 3.5, then of course 3.5 to 4. 3.5 to 4, the maximum GPA. 3.5 to 4. So 4. So this is 3.5. So how many marketers got this? This was say 12 students. These are say 10 students. These are say 20. These ones are 15. I'm going to do this. We don't have to worry about the numbers. Eh? Then this one say are 5. and these are 4. How many? What is the sample size here? The sample size here I selected from the fellows is this. I've selected 66 of them. Let me just add 4. So I'll make this one here 19. Make it a good number. 19. We have 70. That's a small sample. We are going to deal with this. Let me get it's small sample equivalent. Small sample equivalent, small sample, small. Somebody may have decided to use small sample to test that hypothesis stated that side. So small sample, I just change these figures here to say 4, say 3, 5, say 6, and say this is a small sample, 28. So this is a small sample, this is a large sample. So let's test that hypothesis. So mu is equal to 2.7 against HA mu is greater than 2.7 for a large sample. Now, what should guide you when you're testing hypothesis? What should guide you is the test statistic. The test statistic for a large sample is the Z test statistic, which you have written somewhere. The Z test statistic. And the Z test statistic I gave you, I'll bring it there for you. The Z test statistic is here. Z test statistic is here. Just copy it and I bring it there so that you don't have to belabor it. Z test statistic is this one. This one. That's your Z test statistic, this one. So this test requires you to get X bar. Mu, you know. What is mu? Actually, note. Actually, note somewhere that the test statistic is calculated assuming the null hypothesis is true. The test statistic is computed assuming the null hypothesis is true. In this case, mu was equal to 2.7. So we know mu. Mu is 2.7. This one. This is why we collect data. We collect data to get X bar and sigma. N we know. In this case, N is equal to 70. So all I need to get X bar. So I need X cap here. So normal X cap. You write X cap. X cap there. X cap there, of course, we know is equal to is 1 plus 1.5 divided by 2. That's the first X cap. 1 plus that divided by 2. I'm missing a
You've not
bracket.
put one bracket.
I'm missing a bracket here. I'm missing a bracket here. That is the bracket. So that's 1.25. Then we add what? We add what? What's the difference? 0.5, eh? So we add 0.5 plus 0.5 to get that midpoint. You add the class size, eh? Then I do it for all. That is it. Those are the midpoints. I'm doing this so that I get X bar. Then subsequently get sigma. Then I get X cap F. X cap times F. In this case, of course, it is equal to this times this, which is between the first one all the way for all of this. Then I sum them. Sigma X cap F. Sigma X cap F is that. So X bar, I'll write mean, but you write X bar. X bar equals to, X bar, of course, is equal to 141, 161 divided by 70. So it's 161 divided by 70. It is here. That's the mean, 2.3. The mean X bar, this one, is 2.3. Then we get now the standard deviation. Of course, this is X cap minus 2.3 bracket whole square times bracket times F. That's what we're going to do, which is equal to this. Where is X cap? This is x cap minus 2.3 whole squared. This one you know what to do. I don't want to be the right. Squared. Then all squared, bracket that, then of course a bracket times what? Times f. Where is f? This is the f. So that's the first one. That's the first one, which basically is this. For all of this, then I sum. I get 33.08 as the sum of the squared deviation. The sum of the squared deviation is equal to that. Then I get the variance. The variance, again, you write there sigma squared. This one here, squared, sigma squared, this one. So, but we just write variance of x. You write sigma squared, is equal to, of course, is equal to this figure here, divided by, sorry, is actually this figure here, this one, divided by 7. That's the variance. 0. No. That's not the one. Yeah, 0.473. That gives me sigma squared. Then I get the sigma. You write sigma. Me, I'm just going to write S. Sigma is the square root of the variance. So you get the square root of this, the square root of this, which basically is just this, power 0.5. We get the square root. So that's our standard deviation, this. Now we know x bar, we know mu, we know sigma, we know n. So you should substitute. Substitute that z is equal to 2.3 minus 2.7 divided by 0.687 divided by the square root of n. But I'll do it here for you to give you the result. The result here basically is equal to, that is z, z is equal to this. I'll do it for you here. Z is equal to bracket there. X bar is this. Minus, where's x bar? X bar is this, minus what? 2.7. Minus 2.7, times, because you know the square root of n, the square root of 70, so times the square root of, let me just do it here for you now first, Let me just do it for you here. Let me just get the square root of 70 here first. It's 70. Anyway, let me do it here, which is this one. I have this, the square root of 70. Come on, please. 70 square roots, this one. 70 square roots, 0.5. That's the square root of 70. I'm solving for you because you can solve it yourself, but I'm using Excel, so don't worry about what I'm doing here. I'm using Excel. The square root of 70. I need a bracket here. I need a bracket here. Square root of 70. So the square root of 70, and multiply this times what? 2.3 times 2.3 minus 2.7 minus 2.7. I'm calculating the numerator. Divided by what? Sigma. What is sigma? Sigma is 0. This is it. Divided by this. That. So that is my z. When you calculate, you do it yourself. When you calculate z, you'll get minus 4.87. This one, this is what you want. That is the test statistic. That is step 4. You collected sample data to be able to calculate this. Let's start. I do the same for small sample. Let's do for small sample. That's why I use the same data for small sample. Those are your figures for small sample. Those are your figures for small sample. Then, of course, the mean, this one. These are your figures for the measure there. The measure there. Of course, we have here the mean here is 2.5. So I need to come and change this one here to 2.5. Say 2.5. That's the mean. The mean is 2.5. Mean is 2.5. So it's 2.5 everywhere. That's the mean. Any other thing we need to change here? Nothing. Nothing. This is fine. That is fine. The square, that is that. That is that. Variance is okay, which basically is this divided by 28. Then, of course, Z is equal to this, which is just that there. That's fine. Everything else is fine. So for large sample, you got negative this. For small sample, you got this. Now, this is not now Z, but this now T. T is equal to student T is equal to this. Now we have done step 4. You have collected data to calculate the test statistic for both a large and small sample. For both large and small sample. Then we go to step 5. Read for me step 5. Read for me step 5. I want to check whether you are getting. What's step 5 in hypothesis testing?
You identify the rejection.
You set your own alpha. So suppose the test was at 5% level of significance. 5% level of significance. Then, for the large sample test, read, for the large sample test, read from the Z table. Read from the Z table. And I want to bring the Z table here first so that I can show you. Just let me get this for you continuous random, so that you see what you can contextualize what I'm saying. It's a normal distribution.
Prof, just a request as you bring the table, you don't lose the Excel so that you can also share with us.
First. So we are saying that you want to use an alpha of 5%. Let me come back there. I'm bringing the Z, the Z curve, so that you see what I'm talking about. I'm bringing the Z curve there to enable you to see what I'm talking about. I'll bring it here. So the Z table. What you are reading, these Z here are just Z scores. Z is a Z score. So you read, forget about this mu here. I just brought it so that I tell you what I mean. So you are testing at 5% level of significance. And the alternative hypothesis was that mu was greater than 2.7. So I want you to draw this. Draw this normal curve somewhere just around where you are writing from the Z table. What that means is this: when you set up your level of significance and you pick a level of significance of alpha, 5%, 5% is an area under this curve. It's an area to the right. We know the total area in this curve, we understand as normal is 1. The total area is 1. But you only want to take 5%, 0.05. So you draw a line somewhere here. Draw a line somewhere here. Just somewhere here, whatever here, somewhere here. Draw a line somewhere here up to the horizontal axis. Then shade the right of that line. Shade this side here. Shade this side. Draw a line and shade this side. And point here with an arrow, that is the 0.05. The 5%. So that area is 5%. Because we know the total area is 1. So we just take 5% of it. This is the area of rejection. This is the area of commit type 1 error, the probability that you will reject a true null. That's the probability. But for every alpha, there is a corresponding z-score. So where this line meets the horizontal axis, put z 0.05. I mean z 0.05, z. Subscripted, not just 0.05. Z 0.05. You indicate it on the horizontal axis. Indicate it on the horizontal axis. Z 0.05 on the horizontal axis. Somewhere where this line you have drawn here meets this axis here. You put that one Z 0.05. That's what the tails imply. If it is one tail to the right, you chop off 5% to the right. If it was one tail to the left, you would have chopped this from the left. If it's two tails, and I'll mention this now, if it's two tails and you are testing at 5% level of significance, it means you take half this side and half this side. So this side you put Z 0.025, this side also Z 0.025. That's what two tail would mean. But for now, let's conclude with the one tail. So we know that if this is 0.05, then what's the balance of the area here? What's the balance here? What's the amount here? On the to the right, to the left? Which area is to the left now?
1 minus
0.95.
0.9 what?
5.
0.95. That's it. So I go to my, so just note the area you have shaded, because that's important for you. Note the area you have shaded. Then now we go to, and the area you have shaded is to the left. The area you have shaded is to the left of a given value of Z. Is to the left of that line. To the left of that line. Where is the table now? I want to bring the normal table there. The normal table. So that you see how we read that from the line. So I'm giving you the normal table now. The normal table. This part of the reason why I told you to always use the positive side of the table.
Prof, do you mean
But
area shaded to the left or to the right?
So this is my normal distribution curve. This one. This is the table, the normal table. Now, this table gives you areas to the left of a Z. But the area you have shaded on your notes there is to the right of a Z. In fact, you have shaded the unshaded area here, the 0.05. But the body of this table has areas to the left of a Z. So you are not going to look for 0.05 in this table. No. You are going to look for the area to the left of a Z. So you are going to look for 0.9 what? 0.9 what?
5.
5. So I go to the body of this table and I look for 0.95. And it is known, it's a very popular figure, it's known anyway. 0.95 is around here. It is this, either these two. It's not exact. You can either take this or take this. But the most commonly used one is a Z 1.65. So write that. Z 0.05 is equal to 1.65. Z 0.05 is equal to 1.65. That's what I want you to note. First, that's what you have gotten from the table. From the table, you have gotten 1.95. So this one, this Z here, is equal to 1.95. That was step 5. Step 6 is to compare the test statistic Z, in this case the Z, compare the test statistic Z, the one you calculated from the sample, and the Z 0.05. Compare the test statistic Z and the Z 0.05. Now, if Z, if Z is greater than Z 0.05, whatever it is, could be 0.05, 0.03. What I'm saying is that if the Z calculated is greater than the Z table value, this is the Z table value. Let's just write a general statement first. If the Z calculated is greater than the Z table value, then reject the null hypothesis. You reject the null. You are in the rejection region. It means that Z is way beyond the Z 0.05. So you're in the rejection region. So if Z calculated is greater than the Z table value, you reject the null. In our case, Z is equal to minus 4.87, which is less, use the less than sign, which is less than, is less, isn't it? It's less than 1.65, It is,
Yeah.
So this is less than 1.65, and hence we accept the null, and hence the null hypothesis is accepted, and conclude that the null hypothesis is accepted, and conclude that there is no evidence from the sample data that the School of Business is inflating grades for marketing measures. There is no evidence from the sample that the School of Business is inflating grades for its marketing measures. Any differences observed, may be due to other factors. Even some of them chance factors. But it's not grade inflation. That's the evidence you are getting from the sample. That's how you conclude. You conclude on the basis of the problem you stated. Now let's go to small sample. Somebody else could have picked a small sample. The same thing. It is the same thing. We have gotten our T. And you know how to get T? You just replace Z by T. I said you forget about the N minus 1. Just replace Z by T. You get T is minus 1.08. Then we go to step 5. Because we are clear with step. Step 4 is here. We have calculated the T-test statistic. Step 5 is that from the student, so step 5 is from step 5, let's assume still alpha 5% level of significance. And note that the student T distribution, is similar to the normal distribution. It is similar. It is also bell-shaped. It has the properties of the normal, only that is more peaked, incidentally, but it's the same. So note that the student T distribution is characterized by another property called degrees of freedom. Degrees of freedom. Where theoretical degrees of freedom means the number of parameters one has estimated. The number of parameters you have estimated. In this case, you only estimated one parameter. And here it's called the arithmetic mean. So when you have a single sample, degrees of freedom normally denoted by V, DF, normally denoted by D, by V. V. Degrees of freedom, normally denoted by V. V is equal to N minus 1. Is N minus 1. That's the degrees of freedom. So from the T table, from the T table. There's a T table I'm going to show you now. From the T table, I told you this is where we see it. You go read T equals to 0.05, comma, degrees of freedom. How many, what's n here? What's n in this problem? What's n in this problem?
1.
And so what is n minus 1?
1.
Eh?
0.
0.
0.
0.
What is n in a small sample? Small sample. What is n here?
It was 28, no?
20.
Oh, n was 28.
It
Yeah.
was
28. What's 28 minus 1?
27.
27.
27. So 27 degrees of freedom. So you go to the T table and you read this, student T, and read this. This is what you get from the T table. So I go show you the T table. The T table, the student T table. The student T table is here. I'm going to share it just now. Is here. The student T table is this one. This one here. Now I'll give you the structure of the student T table. It is here. Is it? Now this table you must take you must read it. For you, forget about the first row up here. Written probability, community probability. Forget about this. The first row up here. The most important rows are this row and that row. If you are doing a one-tailed test, you use this row. If you're using a two-tailed test, you read this row. In our case, we are on a one-tailed test at 5% level of significance. A one-tailed test at 5% level of significance. And the 5% level, so I go through this, sorry, let me complete. Then this column here are the degrees of freedom, DF. In here are the T values, They are not probabilities, they are T values. So since our test is one-tailed, I read this row. I go all the way until I go where there is 0.05. 0.05 is here. In that row of one-tailed is here. Then I come down to 27 degrees of freedom. 27 degrees of freedom. 27 degrees of freedom is here. That one. So this is the T value at 0.05, 27 degrees of freedom. So I pick this. That's what I pick as my T table value. As my T table value. Then I share Excel. I share Excel. Then we go back this side. That is our T value, right? When this thing counts. That's our T value, 1.703. Then you follow the same procedure. You compare this T value here. If the T calculated is greater than the T table value, you reject the null. Otherwise, accept the null. In our case, this T value is less than this T value. So we accept the null. And we drew the same conclusion we drew under Z above. We accept the null. And that is the test for single mean. The test for single mean. Any question, please? Well, let me go back here. Let me go back here. Let me go back here. To review what we have done.
Prof, do you mind repeating the
No,
statement
I'm not getting
again?
you clear. I don't know what is it, my side or is your side? The layers you talk, I don't know. But I'm not getting it. I'm okay.
I've chatted.
From this side, I'm okay. But I'm not getting it. Literally. Because I'm seeing even my name here is on fully. Yeah? My volume is fully on. And then guy, when you're talking, I'm not getting. I don't know what. But you are getting.
Yes, we are.
Well, we can hear you.
I don't. Anyway, that's how. So
I've
let's just
chatted
watch.
what I'm.
Let's
I've
watch.
chatted what I'm requesting.
You know, he's talking to himself now. I'm not getting you for a fact. But are you getting me? Let me confirm. Or I'm also low. Am I also low?
Look at the chat. Look at the chat.
We are getting you,
Can hear
but
you.
there's a question being asked.
We can hear you.
The chat. Oh, the chat. Oh, yeah, good. Now you are talking. Now you are talking. Now I can go there. That's beautiful. And now the question is, mind repeating the last statement on the T table. The one for the one for what? The one for the conclusion, eh? Anyway, let's go to the T table. Let's go to the T table. This is the T table. This one. I repeat that when you're doing a one-tailed test, you use this. And our test is a one-tailed test. I even know now, I don't know what's happening. The problem is network fluctuation here. I'm seeing it anyway now. I think that's fine. But if you get, as long as you're getting me, I'm fine. So now let's see. So you go here, this you're doing a one-tailed test, and I told you how to know whether it's one-tailed or two-tailed, and you're doing it at 5%, you go for to 0.05. To 0.05, where which is T, where one-tailed 0.05. You go down that column until you go to 27 degrees of freedom, which is here. The number here is the T table value. Then you compare this value here with what you calculated, which was minus something. And since what you calculated is less than this, you accept the null. And you draw the same conclusion you drew under Z. It's the same. You just, I didn't want to repeat it. The same conclusion you drew under Z, about the grade inflation thing. That's what, just copy that conclusion and paste. No difference in terms of the original problem. So that is the T table value. And these two tables are the most commonly used parametric tests. The Z test and the T test. There are others. There are other parametric tests, but these two are the most commonly used. And in this course, these are the only two we are going to use, no other. So this is what I'm just going to review what we have done here. What we have done here. I told you to ignore the n minus 1. Just use n. You're okay. You're okay. Use the details. All these are stories I've just talked about. There's nothing I'm jumping here. I've talked about all this. Rule of the thumb for accepting and rejecting, degrees of freedom. T, again, just use n. Just use n. N, a random sample of 26 accountings scored for 458 in an advanced accounting test with a standard deviation of 20. Is this significantly different from the population average? These are tests for single mean. Mu is equal to 440. Significant difference means not equal to. So your hypothesis will be not equal to this one here. Don't know, we have this. So mu is equal to 440, mu is equal to not equal to 440. Then you have sample data. Sigma, the mean is what? Is 458 with a standard deviation of 20. So X bar is 458. Sigma is 20. N is 26. So this is a small sample. So use the student T test. The student T test, which is here. Again, other things. And that is it. And that is it. So that is the test for single means. Any question, please? I'll not be visiting the chart, That's okay. I'll be visiting the chart. That we are clear. Now, that test we have just done is an appetizer. That's what you do at MBA. It's not the best test. Single mean is not the best. But it is a better input into what you do. Now we're going to look at the next one, which is actually the most critical tests in this program and going forward. And that is test for differences between means. Test for differences between means. So now, difference between means. Let me just share first. Let me look for this first. Test for differences between means. Differences between means. Is the best, really. Test for differences between means. Again, for large and small sum. We do it for both large and small sum. You know, large and small sum. Just like you have done the other one, for large and small sum. This is where your life should be. Have you collect data based on the performance of those students and label them. 1 is equal to male, 2 is equal to female. They have different performances. Then you split it into 2, male and female by gender. You can also split it into 2, probably those working in public sector, private sector. You can also split the population into 2 using any criteria you choose, depending on your problem. The problem is what drives you to partition your population. So those are called independent sample tests. That's one category. The second one is called a dependent sample tests. It has many names. Dependent sample tests or paired tests. Paired test. In agriculture, because agriculture was its origin anyway, is called before and after test. Before and after test. And to me, that's the name I love, the before and after test, which we say we know is dependent. Strictly, this is one population, but with 2 data sets, 2 sets of data. For example, I'll give you an example of what a dependent sample test, a dependent population is. A bank has 8 tellers. 8. Or say 100 tellers. Then customers are complaining. Customers are complaining that the tellers are, that's feedback from the customers, that the tellers, the service time is too low. They keep taking too long in the bank at service, too long at service. And that's a bad picture for the bank. Of course, there are many factors that can lead to service time being slower. The customer's level of literacy. Of course, it also gives the type of transactions they are undertaking, which other customers don't know. It means many factors. But then they are blaming the teller, that the tellers are slow. The bank cannot sack the tellers anyway. They can't sack the tellers. The best the bank can do, they cannot also depend on the claim by the customers. That blanket claim, they can't. So the bank decides to investigate and intervene. Before they do that, the bank decides that probably the tellers requires just retraining. Say, retraining. So they train the customers, the tellers. They train them as an intervention. Or they can give them an IT application. Whatever intervention they want to institute, they institute it in the hope that it will improve service time. Then they want to check later whether the intervention was effective. Whether the intervention was effective. They can't ask the customers. No, they don't have to. They don't have to. What they want to do, what they do, They will collect service time per teller before the intervention. Service time before the intervention. And for the same tellers, they get another service time after intervention. Some will have gotten lower service times, some will still be high, some will be equal, but they will get different service times before and after service times for each teller. So this is just one population. That's why it's called dependent sample. It's one population, paired sample, all before and after. That's the best one, really. Then they use that to test whether that intervention was effective. That is, the service time after is lower than the service time before on average. On average. So that again, we look at here. So we'll start off with the independent sample test. We are going to follow the same steps we have been following for single mean. The same steps. Describe the problem in words. Describe the problem in words. Then state the hypothesis, etc., etc. Now, let me give you the general hypothesis for the independent sample tests. The general hypothesis of the independent sample, which I've designed here. The general hypothesis for independent sample tests, which I've designed here for you. I'm share. And as I said, that hypotheses are written on the basis of the problem. So you have two populations. One is called population 1, the other one is population 2. The null hypothesis is stated from a position of neutrality. So mu1 is equal to mu2. If it was based on the service times, the mu before, mu A is equal to mu B. You can use any subscript you wish anyway. The alternative here is mu A is not equal to mu B. That's the two-tailed test. The second one, there's an error, but I know what I posted to you is there's no error, I had corrected. This one here should be equal to a position of neutrality. Mu1 is equal to mu2 against mu1 is greater than mu2. The same thing. And then the third one, this is for greater than, and the next one is less than. Again, this one is equal to, this one here is equal to mu2 against mu1 is less than mu2. The same thing. The same thing. So you state your hypothesis. So I'm going to go through these slides. I want to take an example to illustrate for you how to perform an independent sample test for the large and for the small sample. Because you have stated the hypothesis, all what's remaining is for us to state the test statistic. The test statistic. So now I want you to take this data set. Take this data, please. Let's write this data somewhere. This is the data. I want to use very simple data here. Very simple. So that we are not complicating life. Very simple. I want to share Excel. Share Excel. Come here. Come there. Excel. Share, please. Excel shared. Then let me just pick this data the way it is for now. For now, I go to this side. Let's paste it here. Now, performance now. Let's talk about performance. These are probably student performance again in terms of independent sample. So the first one here. Let's just call this you measure performance. No, so these are service times. Let's look at service times. Service times. And let's take simple things. So these are a service time of say these are in minutes. 2 to 4. 2 to 4 minutes. Then this one here is say 4 to 6 minutes. 4 to 6 minutes. 4 to 6 minutes. And this one here is 6 to 8. 6 to 8 minutes. 8 minutes. That is what the tellers. The tellers, no, I'm talking about not before. I'm on independent sample, independent, So let's see. Let me say C. I can divide these tellers by gender. So these are the male ones, the male tellers, males. Let's call it M. Male tellers. Those are how long they take at serving customers, serving customers. And of course, this is FM also for males, So this is 6 to 8, and say, I'll just use simple figures, Then 8 to say 10. 8 to 10. 8 to 10. Then say 10. I'm calculating for you, don't have to worry. 10 to what? To 12, 10 to 12, Leave everything else. Then 12 to 14. 12 to 14 minutes. That's how long they took serving customers. Well, 10 to 12. These are the frequencies. Forget about this for the time being. This is what is critical for us here. So let's make it just this, and that is it. So the frequencies, we can say this one say at 15. Sorry, not 15. I just change these figures. Let's say 10, 8, say whatever. I'm just changing so that there's something I want to show you here. Then say 5. Let 5 remain. Then I add. That is the total, 58. That's the critical. Then I just pick the same for female tellers. Let's just assume the same time distribution. Female tellers. Let this remain the same. 28 of them. Female tellers, 28 of them. Then now you want to, there's a claim that female tellers serve faster than male tellers. They serve faster than male tellers. This one, serve faster than male tellers. So this is what you are going to do. You write your hypothesis would have been, if actually you can even make it easier for you. Let's not even call this one XM. Let this one just call this one X2. For male, 2 is for female, M1 is for male. 1 is for male. So you would have written your hypothesis that mu1 is equal to mu2, that's H0, against mu1 is less than mu2. Mu1 is less than mu2. Sorry, mu1 is greater than mu2 because females are serving faster, so their mean service times should be lower. So mu1 is greater than mu2. That would have been your hypothesis. Then you take the test statistic. The same procedure. You state and compute the test statistic. State and compute the test statistic. And I'm going to give you the test statistic. Of course, we had one for the small sample, Z and T. Here we also have Z and T for small and large sample. But how do we decide that it is a small sample and a large sample when they are two? And listen to this now. Very important. For paired samples, these are females. For paired samples, for differences between means, you decide that it is large or small if this plus this is more than 30.
Sorry, we can't hear you. For paired samples? Hello, Prof. You're breaking off.
I think I knew it was an internet issue. I knew. Here at Amatu, you say use data. And that's why you're not even, I was not getting you clearly. Are you getting me now?
Yeah, now we can get you.
Yeah, now it's better.
It's an internet situation here. That's what I was checking anyway. But let's just struggle a bit. You'll get most of the things. So what I've just said that you to check whether it's a large sample or a small sample, you add N1. N1 is the male population. N1 is here, N which is the sigma F anyway. N1 plus N2, N2 is for females, is equal to, is more than 30, more than greater than or equal to 30. That's a large sample. They don't both have to be more than 30. In fact, they could have been less than 30 or both of them. This could have been 25 and this is 28. It is a large sample because 28 plus 25 is greater than 30. That's how you decide. Not to look at on that both must be. No, the sum must be. So let me now give you the test statistic for a large sample. This one. And it means the procedure and how you, and whether you understand the outcome. So what is the test statistic? The test statistic here is given by Z. That is also a Z test, because it is a large sample. It is a large sample. You use Z test. So the Z test is here. And this is where your life should be, I can tell you. This one. That is your Z test. That one. Don't cram this thing. Know how to use it. So now we know what these things mean. X bar 1 means that we must calculate the arithmetic mean for males. For males, arithmetic mean for males, which we can get. This one here, of course, we just pick this and then we can do this. We say 2 here, 2 plus 4. 2 plus 4 divided by 2. Then I add here. What do I add? 2. Add 2. Then I get for all. I've gotten the X bars, which gives me a mean of 7.48. That is X bar 1. That is X bar 1. This is it. X bar 2 is the arithmetic mean here. Again, I just use this. Well, this is the same thing. Yeah, I bring it here. Down there like that. Then we know the distribution. This is the arithmetic mean, 8.143 for females. So that's X bar 1 and X bar 2. Then you note, just like we said in the other one, that Z is calculated assuming the null hypothesis is true. Z is calculated assuming the null hypothesis is true. But remember when the null hypothesis was that mu1 is equal to mu2, meaning that mu1 minus mu2 is equal to what?
0.
0. I repeat, Z is calculated, and even T, assuming the null hypothesis is true, where mu1 is equal to mu2. So mu1 minus mu2 is equal to 0. What is remaining is the standard deviation of the differences. This is the standard deviation of the differences between the means. X bar 1 minus X bar 2. Because this is the differences between the sample means. Where this one here is equal to, this one is equal to sigma 1 squared. What's sigma 1 squared? What's sigma 1 squared?
Variance.
The
Variance
variance.
34.9.
That's the variance for males. That is 1. And the variance for females. What's N1 for males?
58.
58. And N2 for females?
28.
28. So it means here we don't need the standard deviation. We don't need it. You don't need the standard deviation. You don't need the standard deviation. All you need is the variance. All you need is the variance. So what is the variance here? The variance here, because I come here, what's the mean? The mean here is 7.4. So I just do 7.4. I don't want to care about the other things. 7.4. 7.4. Then I do it for all. This gives us a Z value of 8.284. Similarly, the mean here is not 2 point, it's not this. It's not this one here. The mean here is 8.1. 8.1. So I also do 8.1 here. 8.1. Of course, I'm using Excel. Then this one again, I just do this. I come here and I do that. That is it, giving us a variance of 10.41. This is the variance of this. Now I've gotten this. You have gotten this. You have gotten this. So therefore, this one here is what I need. This one, I bring it here, which is our sigma of the sum of the differences. The sum of the differences. I just call it S for my case. But you write this one. So what is it equal to? It is sigma this. It is equal to, I'm calculating it for you. But you substitute. You calculate this one first before you calculate this. Because you need this to get Z. So what is it equal to? It's equal to equal sign, because I'm using the Excel, which is sigma, which is the variance of that one. The variance is this one. Divided by what? Divided by what? 58, 58.
Yes.
Plus what? Plus what? The variance of the other one. What is the variance of the other one? Plus. Plus. What's this?
10.4.
Plus the variance of what? Of females, Which is a bracket here, Which is this, Divided by what?
Yeah.
28,
Yes.
Put a bracket and again. In the square root, Put a bracket again because I'm using Excel. Then that's 0.5. Giving us S is equal to 0.718. That is here, this one here. This one is 0. You can do it yourself using a calculator. This is what it is. This is what you calculate first. Then now you can now get your Z. You can now get your Z. Your Z. Z is equal to, your Z here. Z is equal to, we know what it's equal to, bracket. You substitute here, bracket. Bracket. X bar 1, where is X bar 1? X bar 1 is this one, That's the mean there.
Yeah.
Minus X bar 2, which is this one here. Divide by what? This, which is this one here.
0.7.
That is our Z value. That is our Z value. The Z we have gotten from the sample data to test the hypothesis that females tell us perform more faster than their male counterparts. This is why you collect data to calculate Z. To calculate Z. Then you go to step 5. You set your alpha level of signal, your alpha. In fact, let's say this. Let me just change this test a bit. So that I show you how to use the two-tailed test. Suppose you are testing the hypothesis was that mu1 is equal to mu2 against mu1 is not equal to mu2. Meaning that you only know there's a difference. There's a difference between them, but you don't know the direction of the difference, which is a two-tailed test. I want to show you how to deal with the two-tailed test using this one. Two-tailed. So now the alternative hypothesis is now two-tailed, not equal. So if that's the case, and you are testing at 5% level of significance, then you go to the Z table. You go to the Z table. I'm going to write this here because this is important. Because it's not how the way you're going to read it. You go to the Z table and read Z. Come here. You read Z 0. It is 5%. So you divide 5% by 2, then 0.025. That's what you look for in the table. That's what you look for in the table, that area. Which area, you, of course, you're not going to get in the table. You are going to get the area to the left of it, which we saw last time. Eh? So I want to share the Z table. The Z table. So we go to the Z table and look for that value of Z. That value of Z. This is the Z table. Now what you have done here, this is a two-tailed test. So we simply take half of the level of significance. So the shaded area will be 0.025, which is equivalent to this unshaded area here. The area you're looking for really is not this area because of the table we are using. We are looking the area to the left. So we are going to look for the area 0.975 from this table, not 0.025. So I go down and I look for 0.975. It's also known, a very popular one. 0.975 is here. Where's 975? 5 is there. 5 is down there. 0.975 is here. Is here. This one. That's the closest, which is 1.6 what? 1.6, 1.65. 1.65. 1.65. So that value then also is equal to 1.65 for 2 tails. 1.65 for 2 tails. For 2 tails is 1.65. So we go here. Quick share here. So this value here is 1.65. This one. 1.65. Then the same procedure. You compare this with what you calculated. What was it? This. If this one here is greater than this one, you reject the null. Since in our case, this one is less than this one is less than this one, we accept the null. We are saying that there is no difference. There is no difference between the service time for males and females. Any differences you're observing really is by chance. By chance. Gender is not an issue here. Gender is not an issue because you are accepting the null. There must be other factors that makes that may be bringing that claim that there is a difference between male service times and female service times. Am I clear, please? So that is a large sample. Now let me do for you a small sample. A small sample. I just pick the same data. We don't have to waste time here. Pick the same data and bring it here. Small sample. Now we ensure that the N1 plus N2 is less than 30. So I just change this. I change this to 2, 5, say 2, 4, 1, 5. That is 14.
Doc.
That's 14.
Yeah.
Just use the same data. The same data.
There's a question.
The sample sizes. Pick the same data. This says for small sample. Small sample. So small sample there for males are 14, and let's ensure that these ones are also less than 30. Let's just make this one here. We just make this one here, say 2, 1, say 3, 1. That's 29. 29. 14 plus that's 29. So these are small sample. A small sample because the sum of N1 plus N2 is equal to, is less than 30. Procedure again. You have collected data to compute the test statistic. So what's the test statistic here? The test statistic here is the t-test statistic. the t-test statistic, just like the other one. So what is the t-test statistic? It's the same, but I'll give you the t-test statistic. I'll give you the t-test statistic, which again, I repeat, don't cram these things. Don't cram them. It will not help you cramming them. The t-test statistic. The t-test statistic looks like as follows. As follows. I'm giving it to you just now. Just now. It's only differs on the sigmas. The t-test statistic. I'm only give you one version of the t-test statistic. And this is this. See, this is similar to Z. This is similar to Z, this one. This one here is the one different, this one. This, of course, assuming equality of variances. I don't want us to go through those details. And there's one for inequality of variances. Just use this to perform the t-test for now. So the same thing. You calculate t assuming the null hypothesis is true. Then you get this. This one here is the one which is equivalent to this one. This one. Sigma x cap. Sigma x cap. That's what I want you to note here. We should have changed this. This one here is just divided by sigma s cap. This one. Where sigma s cap is n1 minus 1 into s1 squared. S1 squared is the variance of the sample. S1 is the variance of the sample. S2 is the variance of sample 2. N1 is the sample size here. N2 is the sample size here. So here we have gotten our x bar 1. X bar 1 is here. 6.658. X bar 2 is here. There. That's x bar 2. That's x bar 2. Mu1 minus mu2, 0. This one here is equal to, and we know what is S1 squared. S1 squared is here. I'll just call it for this S1 squared is here. S1 squared. Squared. With the square on top. S1 squared. S1 squared is this variance. It's the variance here of the first one. And the variance here, of course, we know this one here, of course, that one there is not that. This one here is 6 point what? 6.9. 6.9. The current mean, 6.9. And for all, then we use this to get this, which is just this one here, divide this one here, divide by 14. That is the variance. We don't need a standard deviation here. Then x bar 2, so that's the S1, 2, S1, S2 squared, S2 squared the same. That's for the females. S2 squared, the same. For the females. Because those are subscripted things. Like even this one here, you need to change this to 6.9 also. 6.9. This is a 6.9. 6.9. That's my date. Then you come here. Of course, this 6.9, that's what an issue here to me. Because this is Excel. Under that, you get 179. We divide this by 15. By 15, we get what? The variance of 11. Here we got a variance of 8.26. Then now we calculate this. I said this one here should be replaced by this. This one. This is for the equality of variances. You need to use this here. You need to use it there. Then you are safe all the way. You're safe all the way. However, if you are that's equality of variances. But in fact, what I could even do is to make your life easier. I'll just make your life easier when you are assuming equality of variances. Equality of variances. Let me just make your life easier. But it's very easy. Very easy. So this one here is when variances are equal. When variances, you assume equality of variances. Note that, when you assume equality of variances, you get this. Then for you to get this one here, this one, you need to get this, that one. So these three are for equal variances, these three. So what this tells you, you first of all get this one, which is n1 minus 1. What's n1 minus 1? n1 is 14. 14 minus 1 times s1 squared. S1 squared is what? 8.267 plus n2 minus 1. What's n2 minus 1? 15. 15 minus what? 14. 14 times what? Times what? S2 squared, which is 11.59.
11.9.
Divided by n1 plus n2 minus 2. n1 plus n2 minus 2 is 14 plus 15 minus 2. 29 minus 2 is 27. You will get this figure. This one. So this figure is the first one you calculate. If you are assuming equal variances, and that one you always check, you always note, equality of variances. That is in this test, equal variances. That the variances for male and females are assumed to be equal. So this figure here, this one, will be equal to, I'll just do it for you here. This one here is equal to n1 minus, this one here is 20 what? 20? This is 20, no, this is 13,
14 minus 1, 13.
Yeah, which is 13, 13 minus what? 13 times what? It's actually 13.
8.267.
8.2.
Times that one,
6.
8.27.
Then we add what? We add
You
what?
add 14.
14,
Yeah.
14.
We add 14
Yeah.
times what?
Times 11.
Times
11.9. 11.
Times this
12.
one, isn't it? This one, That's the numerator,
Yeah.
Then divide by, what is n1 plus n2? Minus 2 is 27, isn't it?
27.
27. I'm using Excel so that, you can substitute yourself, so that you just know the procedure of doing this, What's this now, please? So let me just put
You have
another
a bracket that is not closed, huh?
looking for.
The 27, the
Bracket.
27.
The
So this one here
N2
is 13 times this plus this times this divided by that. How many open brackets? 1, 2, 3.
You remove the brackets.
1, 2, 3. Close bracket.
It is okay now. It is okay now, Doc.
Are you talking to me or because I'm not getting you, please?
It is okay now. The brackets are fine.
0.25.
Power
0.5.
0.5.
Yeah.
So if you do power 0.75, this is what you get. This is the square root of this. You get this figure here. You get that figure. And I'm here, equality of variances. This is use this relationship. So this is what you get. Then from here, to get this, you get this. And this one is equal to, and it's here, is equal to bracket of what? This figure, which I've calculated, times 1 divided by
14.
14. 1 divided by 14,
Yes.
Plus what? 1 divided by 15.
15.
Bracket divided by 15.
Come on, sorry about this. Sorry about that. So what is, I'm going to do this. What is 1 over 14? 1 over 14, let me just do this aside first. Let me just get this. 1 divided by 14 is that, And then 1 divided by 15 is that,
Correct.
Those are figures we require. 1 divided by 14 is 15.
15.
Is that?
Formatting.
Is that one
The
there?
issue.
which gives you this figure here. So I'll just put them aside. I want to use them, substitute them. You can substitute in your calculator. So this figure here, we are saying is equal to this figure you have calculated, which is this one here. That one. Times what? Bracket. This figure, bracket, eh? This figure here, plus that figure, bracket, square root.
0.5.
Bracket.
Close bracket.
And we are done. There you go. Good.
Close
So that
another bracket.
you get 3.9.
Guys, where are we getting the 0.5 from?
3.96.
0.5
is the variance of the difference. This figure here.
is the significance, 5% significance.
Where is the
Excuse me,
formula?
are you
of
talking
16
or
power
you are
0.5?
There's a question,
no,
Prof.
Hearing you, you not
question.
hearing you.
Oh,
Prof, there's a
okay.
question. Glow 0.5
Hello?
is a factor in Excel for square
Yes,
rooting.
Prof.
Are you, because I'm hearing you're talking, or I mean, are you asking a question?
We're
No,
asking a question.
Are you asking
It's
a
a
question?
question.
Yeah, I'm
Yes.
lost.
Yes, question is?
Yeah, please click on the 10.66 up there.
You know, raise your hand, your voice again like you are talking, because now you're down a bit.
I'm
chat,
saying.
good. A good chat, eh?
Raise hand. We won't hear even if we raise. Prof, can you hear me?
He's saying you go, you
You're saying you use
type
the
on the
chat, eh?
chat.
Accept that
Okay.
calculated, eh? 0.5, eh? I'm not seeing anything here.
We have answered her.
I'm not
It's
seeing
long, I'm
anything.
typing.
What are you
Glow
asking?
type.
I'm typing.
You know, the first thing I stated when I started today is that you set your own level of significance. Yours, eh? Your own. And I said, and I clearly said that business normally use 5% level of significance. Eh? In others, pure sciences, they use lower one, 1%. That's what I said, eh? True?
Yes.
Yeah, so I'm you set
Nilikuwa
your
kwa
own.
hiyo
But let
formula.
me
In the
also tell you, in
formula.
future, as you read, you'll be seeing this level of significance, what people use it at different times. At different times. Even here at the university, you know, most people just use 5% level of significance. But of course, what I think you could be asking is that, where do they come from really? But that's mathematical. Mathematics. Your statistics is math. To set level of significance, to establish them. Because the level of significance is established. That's why I was telling you, more in business, most people use. And that's what I want you just to use that culture. Then you get your probability of committing type 1 error. That's the level of significance. So now I go back to repeat what I was saying here. Because I know there was some. What I was saying here, for independent sample tests, for small samples, you use these three relationships. The first one you use is this one here, which is basically is actually called the pooled mean, the pooled variance, pooled standard deviation. You have pooled the two to come with up with one. Then you get now you get this one here under for T. This one for T is this one you have just calculated times the square root of 1 over n1, which is 14, plus 1 over n2. You multiply those, you get this, that one there. Then now you substitute this here. This is what you substitute here.
Brooke, you're not
mu1
sharing your
minus
screen.
mu2 is equal to 0. Because T is calculated when assuming the null hypothesis is true. The null
Prof, your
hypothesis
screen
is
is off.
true. This one here.
Oh,
Then of
Prof,
course you know this
you're
one.
not
You have
displaying
calculated this. It is here.
your
6.857.
screen.
X bar 2 is here. 6.867. Then you get your T.
Sorry, Prof, we can't see the screen. We can't see the screen.
Eh?
We can't see
you
the
can't
screen.
see. Because
Yeah.
I left the other side without going back. I'll repeat what I've just said. The problem with this technology things. Let me just share Excel. And I'll tell you what I'm saying here. What I was saying here is that based on this one here, first of all, you get this. This is the procedure. You get this, which is our case is that. Then use this to get this, together with, of course, N1, which is 14, N2, which is 15. We got 3.96. Then we substitute this one here. The standard deviation of the difference. Then we have sigma 1 bar we gotten is 6.857. Sigma 2 bar, so the X bar 2 is what? 6.867. Of course, mu1 is equal to mu2 at null hypothesis. So this is 0. Then you use this to calculate your T. That is your test statistic. That is your test statistic, assuming equality of variances. Of course, there's a relationship for an equality of variances, which is the same as the Z anyway, the Z1. But let's use this to illustrate. So you have gotten your calculated your T calculated from the sample. Now you go to the T table. You go to the T table. The same thing we did. You go to the T table and read from the T table, from the T table, from the T table, from the T table. Read. You read the following. T, don't write fast. Remember this is, we are doing here the what? The two-tailed test, at 5% level of significance. So I said we take a half of that, with T 0.05. This one I'll write for you here, of fully, 0.05, comma, degrees of freedom. Here, degrees of freedom is not N1 minus 1, but degrees of freedom is this one here, N1 plus N2 minus 2, which is N1 plus N2 minus 2. That is the degrees of freedom for independent sample tests. Independent sample test, which is basically the difference between mean sample. The difference is between means one. So I'll do this for both. You need subscript all these things. This is N2. This is N2 minus 2. Minus 2. And of course, this one also, we need to just bring this one here. This one here is the same. It's also subscripted. So you go to the table, and that's what you look for. You look for that from the table. This is this. But critically, pay attention on how you get this from the table. Let me make it larger. This one larger, so that you can see clearly. Make this one larger. Probably 16. Like that. So this is what you look for from the table. This one's here. Need to be subscripted also. Subscript. But they're just below T. That's what I'm saying. Subscript all of them. It's N1 plus N2 minus 2. So that's what you read from the T table, which results into the following. This is what you are going to look for. You are going to look for, this is what you are going to look for. We know our 0.05. So this is what you are going to look for in our table. Please. What you are looking for in our T table is this. T 0.05. No, 0.025 because it was two-tailed test. 0.025, 25, 25, because it's two-tailed test. This is also 25. Take half of 0.05. Then the level of significance, N is 14, N2 is 15, so 15 plus 14 is 19, 29, 29 divided by 2 is 27. So we are looking for this from our table. We go to the T table, and that's what we look for from the T table for a two-tailed test. And I want to show you how to read a two-tailed test from the T table. From the T table. So let's go to the T table. I'll get you the T table. And then share the T table. And please see how we read it from the table. When it is two-tailed, this is how you read it. Here's the T table. Now we use the lower tail, this one, two tails. Two tails. Remember what you are looking for there is T 0.025, 27 degrees of freedom. That's not what you're looking for here. What you're looking for here, which is equivalent to that, is two tails T 0.05, this one, two tails. It implies you're actually looking for the 0.025. The 0, which you can see up here. You're actually looking at 0.025. You divide it by 2, and then, but here you read it, you read the entire level of significance under two tails. But if you want to use one tail, then of course you just use the 0.025 there, which is here, up here. But I would encourage you, if you just use this, then use 0.025, 0.05, two tails through. Then you come down up to 27 degrees of freedom. 27 degrees of freedom are here, is here. So that is the value you are calculating. You get from your table. The value you get from your table is that one. Then I come here. Then we go here. So this figure here is this one here. That's our figure. 2.052. That's the T table value. The T table value. That's the T we have read from the table. The T we have read from the table. Then you compare that T you have read from the table with what? What are we comparing it with? Have we gotten it anyway? With what? We had gotten a figure, you know. So you had gotten a figure.
Calculated. 3 points.
It was what?
Yeah. 3.96.
Yeah, this one here. No, not that one. I know we have gotten a figure, but you know the figure. What you do, compare that figure we got from here with this figure here. If that figure we got from calculation is greater than this figure, you reject the null. Otherwise, accept the null and draw appropriate conclusion. And draw appropriate conclusion based on the problem. You draw appropriate conclusion based on the problem. The same procedure. There is no difference in procedure. No difference. Now that is the independent sample test. That's the independent sample test manually. Manually, we have done it manually. But we'll also show you how to do this in Excel. We'll also show you next week how to do this in SPSS. So this is our independent sample test. So now let's see what we have. This is what I've done.
I think Michael is the profanous here.
Procedures we have done. A random sample of 17 police officers in whatever has a mean annual income.
Some of us have deeper ones.
A deviation of that. Now this again, independent sample test for small sample. For small sample. So the procedure is here. Procedure you can check. Now I don't want you to bother about testing for proportion. This one
Alice,
is on consumption in future. You are
Yes.
you check how you
you
test.
can help us call Prof to answer the
Will be
question.
the same. Same procedure as
Prof.
the Z. Sorry, as the mean. The
Prof.
normative mean.
Raise your hand so that he sees.
So then what?
Anasikia Mike.
So now we are explaining equal variances. Now equal variances simply means that variance is variability. So you're assuming that if the variance of the male service time is 6, the one for female is 6. Here you cannot see how to test for equality of variances. There is a way for testing that variances are equal. And that will show you in SPSS. This is a good question, Mr. Again. That's a good question. Of course, manually, I cannot show you how to test for equality of variances because it employs proof. But when we go to SPSS, I will show you how to confirm that variances are equal or equal. But if we are just doing calculations, we'll be told to assume equality of variance or whatever variance or whatever nature of the variance. So that's an important question. When you go to the system, will show you how to test for it. Even Excel does not test for equality of variance. It does not test for equality of variance. Now, so this is not what it means. That equal variances does not mean they are exactly equal. It means is the difference significant? There could be some difference, but that difference may not be significant. So they don't have to be equal, that this one is 6, this one is 8. No. Is that difference between variances significant that it has an impact on whatever the means that you have calculated? So that's what it's not that they must be exactly equal. No. That's what I'm trying to tell you. This question will be answered better when we show you how to test for equality of variances, where you will see the variances are actually unequal. But the test is showing you that that difference is not significant, and hence you can assume equality of variance. I hope that one answers you, for now.
Yeah.
Any other query, please? If there's no query, then we only have one more parametric test to undertake, and that is next week, and that will be the dependent sample test. Then we do a chi-square. I'll show you, so that within the next 2 weeks we are done with this course. But we'll have to run through the SPSS. You have the data already. We'll show you how to do this in SPSS. We'll show you how to do it in Excel with its limitation, and then interpret that result. So that's more. That's when of better value in research. So with that, then we stop there. You can stop there today.
Prof,
Yeah.
if you can hear us, just a request to share the Excel with its formulas as it
We
is.
stop there. Stop.
Whoever can.
So Anna, I'll send you the YouTube
And
for
please
this
text.
thing, and then you can.
Okay.
You can send.
And
Okay.
please text him to include the Excel.
So I'm exiting.
He has said he will send everything.
Don't exit,
I'm
Buana.
exiting.
Wait.